In this diagram, we're looking at a made-up population of 5 people. Each person in the population has a certain age, and the mean age of the population is 20. If you added the 5 ages and divided the total by 5, you would get 20. The standard deviation of the population is 1.58. Let's say that I randomly select a sample of 2 people from the population. I record their ages, and I calculate the mean age of the sample. I add the 2 ages, and I divide the total by 2. In this situation, there are 10 possible samples. One of them will become the actual sample. I might get person 1 and person 2. I might get person 1 and person 3. I might get person 3 and person 4. Or I might get one of the other possible samples. These 10 possible samples make up the sampling distribution in this situation. I said that the mean of the population is 20. The mean of the sampling distribution is also 20. If you added the 10 sample means in the sampling distribution and divided the total by 10, you would get 20. That's because when a sample is randomly selected from a population and a sample mean is calculated, the mean of the population and the mean of the sampling distribution are the same number. Mu and mu x bar are the same number. Since I have all the possible samples laid out for me in a diagram, I can actually use the diagram of the sampling distribution to find a margin of error. For example, if I wanted to find the 80% margin of error, all I would have to do is mark off the middle 80% of the sampling distribution, and then find the distance from the population mean to the lower end and the upper end of the middle 80%. Let's actually try to do that. There are 10 samples in the sampling distribution, so the middle 80% would be the middle 8 of the 10 samples. I just marked off the middle 8 of the 10 samples, so I just marked off the middle 80% of the sampling distribution. The 8 samples in this middle area make up the middle 80% of the sampling distribution. This lowest sample is the lowest 10%, and this highest sample is the highest 10%. Each of these 3 areas has its own probability. When I randomly select my sample of 2 people, and I calculate the mean of my sample, I have a 0.10 probability of getting a sample from this area. I have a 0.80 probability of getting a sample from this area, and I have a 0.10 probability of getting a sample from this area. Since I have a 0.80 probability of getting a sample from the middle 80%, I'm 80% confident that I'll get a sample from the middle 80%. I'm 80% confident that I'll get a sample somewhere in this middle area that goes from 19 up to 21. Since the middle 80% area goes from 19 to 21, the 80% margin of error is 1. The 80% margin of error is just the distance from the population mean to the lower end and the upper end of the middle 80%. So overall, I'm 80% confident that I'll get a sample mean somewhere within 1 of the population mean. I'm 80% confident that I'll get a sample mean somewhere between 19 and 21. Now if I wanted to find the 60% margin of error, how would I do that? Well, if I wanted to find the 60% margin of error, I would need to mark off the middle 60% of the possible samples. There are 10 samples in the sampling distribution, so the middle 60% would be the middle 6. 6 out of 10 is 60%. I just marked off the middle 6 of the possible samples, so I just marked off the middle 60% of the sampling distribution. These 2 samples make up the lowest 20%. These are the middle 60%, and this is the upper 20%. Once again, each area has its own probability, and I'm 60% confident that I'll get a sample somewhere in the middle 60% area that goes from 19.5 up to 20.5. Since the middle 60% area goes from 19.5 to 20.5, the 60% margin of error is 0.5. The 60% margin of error is just the distance from the population mean to the lower end and the upper end of the middle 60%. So overall, I'm 60% confident that I'll get a sample somewhere within 0.5 of the population mean. In other words, I'm 60% confident that I'll get a sample mean somewhere between 19.5 and 20.5. Usually, a margin of error can't be found using this method, because usually you don't have all the possible samples laid out in front of you. Usually you have to use a different method to find a margin of error. We'll use that method in a later example. For right now, let's imagine that I'm taking a random sample of 3 people from the population, and I'm calculating the mean age of the 3 people. In this situation, there are 10 possible samples. Once again, this time each possible sample is a sample of 3 people. If I want to find the 80% margin of error, all I have to do is mark off the middle 80% of the samples and find the distance from the population mean to the 2 boundaries. In this situation, the distance is 1.67, so the 80% margin there is 1.67. If I want to find the 60% margin of error, all I have to do is mark off the middle 60% and find the distance to the 2 boundaries. In this situation, the distance is 0.33, so the 60% margin of error is 0.33. I said that usually you can't find the margin of error using this method. That's because usually you don't have all the possible samples laid out in front of you. If you don't have all the possible samples laid out in front of you, you can still find the margin of error if you know that the sampling distribution has a normal curve or a normal distribution to it. If you know that the sampling distribution is normal, then you can actually use the shape of the normal distribution to find a margin of error. Let's do that in our next example. This is a more realistic example in which I'm taking a random sample of 40 people from a large population that has a normal distribution. I'm recording the ages of the 40 people, and I'm calculating the mean age of my sample. In this situation, the sampling distribution is normal because when a sample is randomly selected from a population and a sample mean is calculated, the sampling distribution is normal if the population is normal or the sample size is 30 or larger. This rule is called the central limit theorem. In this situation, both are true. The population is normal and the sample size is 30 or larger, so this sampling distribution definitely has a normal shape. Since the sampling distribution is normal, we can use the shape of the normal distribution to find a margin of error. The first step is to find a value called the standard error. When a sample mean is being calculated, the standard error, or sigma x bar, is just the population standard deviation divided by the square root of the sample size. I need to divide 1.58 by the square root of 40. When I do that, I get 0.25. That's my standard error. Next, we need to use something called the z-score. Before we do that, I want to give a quick recap of what a z-score is. In a sampling distribution, the population statistic, which in this case is the population mean of 20, has a z-score of 0. The number that's one standard error above the population mean has a z-score of +1. The number that's one standard deviation below the population mean has a z-score of -1. And 2 standard deviations above is +2, and 2 standard deviations below is -2. So the z-score is just a multiple of the standard error. Now why does this matter? Well, when a sampling distribution is normal, it's possible to take any 2 z-scores and find the percentage between them. For example, in a normal distribution, or when the sampling distribution is normal, 70% of the samples fall between these 2 z-scores. That means that if I want to find the 70% margin of error, I can make use of this z-score of 1.04. Also, when the sampling distribution is normal, 95% of the possible samples fall between these 2 z-scores, which means that if I want to find the 95% margin of error, I just need to make use of this z-score. If I want to find the 95% margin of error, all I do is I take this z-score and multiply it by the standard error, and I get the answer. If I want to find the 70% margin of error, I just take this z-score and I multiply it by the standard error, and I get the answer. So I'm 70% confident that I'll get a sample mean somewhere in this area. Let's now look at an example involving a proportion. So let's go back to an example involving a small population. This population is 50% male, so the population proportion P is 0.5. Let's say that I'm randomly selecting a sample of 3 people, and I'm calculating the proportion of males in my sample. I'm calculating the fraction of males in my sample. In this situation, these are all of the possible samples of 3 people that could be selected, and each possible sample has its own proportion of males. This sample has no males. This sample is 100% male. Each of these samples is 2/3 male, and each of these samples is 1/3 male. The population proportion, which is 0.5, is at the center, and if I mark off the middle 90% of the possible samples, then I can find the 90% margin of error. All it is the distance from the population proportion, 0.5, to the 2 boundary points. In this situation, I was able to find the margin of error visually because I had all the possible samples laid out in front of me. If they weren't all laid out in front of me like this, I could still find a margin of error if I knew that the sampling distribution had a normal curve or a normal distribution. Let's look at a situation in which the sampling distribution is normal and it is possible to find a margin of error for proportion. So in this situation right here, the population is 60% male, so the population proportion is 0.60. I'm taking a random sample of 40 people. I'm recording the genders of the sample, and I'm calculating the proportion of males in the sample. A sampling distribution, when a sample proportion is being calculated, the sampling distribution is normal if n times p and n times 1 minus p are both at least 10, and that is true in this situation. So the sampling distribution is normal, and the population proportion is at the center, which means I can make use of the normal distribution to find the margin of error. For example, if I want to find the 95% margin of error, I just multiply this z-score, 1.96, by the standard error, which I calculated here, and I get the answer. It comes out to 0.16. So there's a 0.95 probability that the sample proportion will come out to somewhere between 0.44 and 0.46 male. Let's look at one more example right here. In this situation, the population mean is unknown, but I do know the standard deviation, and I'm taking a random sample of 40 people. I'm recording their ages, and I'm calculating the mean of the sample to estimate the mean of the population. I can still calculate the margin of error in this situation. Let's say that the sample mean comes out to 19.7. If I want to calculate the 95% margin of error, all I have to do is find the standard error and then multiply it by 1.96, and I get the answer. What this is telling me is that when I randomly selected my sample of 40 people and I calculated the sample mean, I had a 0.95 probability of getting a sample with a sample mean within 0.49 of the population mean, somewhere in this area, right here. And in this situation, what I can also do is take my sample mean of 19.7 and add and subtract the margin of error. If I do that, I get something called a 95% confidence interval. If I take the sample mean and add and subtract the 95% margin of error, I get 2 answers, and the interval between them is a 95% confidence interval. And this 95% confidence interval includes the population mean inside of it, as long as my sample mean of 19.7 is somewhere in this middle area, within 0.49 of the unknown population mean. Now, if my sample mean is more than 0.49 below the population mean in this tail, then the population mean isn't captured in my interval. And if the sample mean is up here, up more than 0.49 above the population mean, then the population mean is also not captured inside the interval. So what I would say is I'm 95% confident that the population mean is somewhere between these two numbers right here.